Does anybody here listen to the podcast How I Built This? Okay, so three people got the joke. Anybody here a fan of Friends? The one where things happen? This is totally not the right demo for my jokes. This is going to be a painful 15 minutes. I want you to recall 2010. 2010 was a year of disasters. There was the Deepwater Horizon oil rig explosion and oil spill. There was the Wall Street flash crash. There was the Mount eruption that spewed ash all over the skies of the North Atlantic. And then there were those freaking vuvuzelas at the World Cup in 2010. I still have a ringing in my ears from those. And then, bringing it back to me, when I was just a software engineer at Indeed, I took down Indeed.com and Indeed.co.uk and Indeed.es and Indeed.ca and Indeed.fr. We had a few sites for me to take down. To understand what happened here, let me take you back to the much more primitive Indeed architecture back in 2010. We had a front-end web app that served multiple purposes. It would serve the home page, it would serve our job search, it would serve the view job page where you looked at a single job in detail. If you signed up for job alerts, our email product, it would serve that. It also served a health check for load balancers and our dynamic DNS. All of those would go through a hardware load balancer and get distributed to any one of the web application server instances in the pool. Behind that, what we had was, in theory, service. We had this search service. We had exactly one of these deployed for each one of the web app instances, and it only served requests for that one web app. It was pretty simple to set up, but there were obvious problems with scalability and reliability. It was just like the first straightforward stab at separating these two components. Now, what we didn't want was an architecture like this, where the web app, in talking to the services behind it, would go through a load balancer that would get distributed to the backend services. We actually had this with one service called doc service, and it meant we had an additional point of failure in the load balancer, which was not a cheap piece of hardware, and then we also had double the network traffic. So we were looking for something different from this as we built a true service-oriented architecture for all of our systems. That's where Boxcar comes in. Boxcar was our client-managed system using direct client-server connections in shared connection pools. It was implemented on TCP/IP instead of a higher-level protocol. It would reuse connections for multiple requests to avoid the setup and teardown. And it was designed to be resilient against failures. If you want to know more about this, you can go to go.indeed.com/boxcar, where there's a deeper dive into the system and protocol. Visualized, what we wanted to deploy was a system where every web application server instance could talk to every search service instance. There would be a connection pool in every web app instance, and requests would get routed to the backend services using connections from those pools. So if one of the service instances went away, each web app could still serve requests using the others in the pool. The first thing we did was port that doc service to Boxcar. That was the first one with the HTTP-based service API. And we deployed it, and it was a success. So emboldened by this, got a little bit more confident, and ported the search service to Boxcar and deployed it. And it looked like a success initially. And then everything blew up. And our on-call was wondering, what happened? I looked through the logs the next morning, and I saw a lot of messages and exceptions like this. Server sent payload with claimed size of 1,000,056, disconnecting, over and over and over through the logs. In fact, it happened 1,144,494 times. That was a lot of log space. Mystery number one in investigating this. Why was it failing on payloads that were greater than 1 megabyte? This was greater than 1 megabyte by 56 bytes. Well, the Boxcar protocol reduced to one very simple aspect. There was a declared message length, and then there was a payload of variable length based on what that first value was. When a Boxcar server or client received a message, it would read that length, it would allocate a buffer according to the size that it was specified, and then it would read the entire payload into that buffer. I should have read this book. The dummies part, that was me. I hadn't done any TCP level programming to this point in my career. I'd done a lot of stuff at the HTTP layer. I'd done non-networked applications. This was the first time I was directly working with TCP. And I wasn't really sure of myself. And I was figuring it out based on some Java docs and some crib together man pages, but I didn't really have like a comprehensive view. I didn't have a whole lot of confidence that I would get things right with big endian versus little endian and reading the bytes in the right order, getting the sign bits correct. And so I put in a safety check. I made the code assume that any payload longer than 1 megabyte was my bug. So abort the request handling in order to avoid an out-of-memory error. Given my lack of experience with TCP, I figured there was a really good chance I would accidentally tell the server that there was a 1 gigabyte payload because I screwed up some of the bit banging or the signs or whatever. And I didn't want that service to allocate a 1 gigabyte buffer, not to mention doing it repeatedly over multiple requests, because that would take down Indeed.com. So where did that 1 megabyte come from? I made it up. It seemed like a good number. So lesson number 1 is measure actual values instead of inventing arbitrary thresholds. I was convinced that there would be no legitimate payload that would be anywhere near that size. Nice round number? Sure, put it in there. Turns out I was wrong because there was a payload as demonstrated 1,144,494 times in the logs. There was a payload that was greater than 1 megabyte. Then there's mystery number 2. A 1 megabyte response. But we only show 10 jobs on a single page. And even the longest job description and the most metadata about a job is going to be maybe 10 kilobytes. So how would 10 jobs from more realistically 1 to 3K, how would that exceed 1 whole megabyte? Let's take a look back at this front-end web app. It turns out that there was more that was going through the web app and to the back-end services than just those searches. There was the home page. It was only serving job counts, and so it was fetching 0 jobs. It was just trying to see how many jobs there were for your most recent query. Job search, as I thought, served 10 jobs at a time. View job page was exactly 1 job. Job alert signup had nothing to do with searches, so 0 jobs, didn't even go to that service. Then there was this health check. Some of my digging into the system traced it back to this health check. What was the health check doing? The health check was requesting every job ID in our entire search index. And if you get enough job IDs, that's going to get over that 1 megabyte limit. I can't tell you exactly how many job IDs that was because of the way the integers were encoded, but clearly we got there. So lesson number 2, always limit how much data you request. Be very, very careful if you're going to say, give me everything. Maybe start by saying, tell me how many you have, and then request it in batches, so you don't run into something like I did. Mystery number 3. Why did bad health check requests take down everything? How come it wasn't just the health checks that were failing? Well, Boxcar uses one connection pool for every request, whether it's homepage, job search, view job, or the health check. And so when the health check was affected, it would affect those other requests as well. They used the same connection pool. And if you look at the request history for a single connection, you'd see a number of searches, maybe a health check, a search, some view jobs, searches, health checks, view jobs, all intermingled. as each one passed serially over that same connection. Also, I was building for resilience. The idea is, if at first you don't succeed, try again, as embodied in this while loop. And Boxcar would assume that errors were local and transient. So it would close the connection on any kind of exception and retry with a different connection. That seemed pretty reasonable, right? I got a flaky response from this server. Let me try again, hope I get to a different server that actually gives me what I need. We had good intentions, but these were bad outcomes. We'd have a pool of 5, we would grab the first one, we would try, we'd get an error and we'd close it. We'd do again with the second one, try, error, close. Third one, try, error, close. Fourth one, fifth one, until that connection pool was empty, because we had rotated through every single connection in the pool and gotten a failure each time and closed it each time. That meant the health check couldn't be served, but it also meant the view job page couldn't be served, and the search itself couldn't be served. It was a combination of a shared connection pool, infinite retry, a persistent error rather than the transient error that I assumed, and this close on error behavior, which led to this empty connection pool and an inability to serve any requests at all. So lesson number 3 is bound all loops. Even if you think you want to do something indefinitely, just pick some number where you think, I'm never going to loop that many times. Okay, put it in there, and you can either be smug and satisfied when you never ever hit that loop condition, or perhaps you can learn something about your system that you didn't understand before. Then there's the lesson not learned, isolating health check requests from real traffic. That would seem like a logical situation here, right? We had this dysfunctional behavior in our health check, and it leaked into our other use cases. We don't want the health check taking down real user searches, right? But we didn't learn this lesson because that would actually lead to undesirable consequences. We want the health check, which serves our load balancer and our dynamic DNS, we want it to simulate as closely as possible the experience that our job seekers have. So that means if the search service, if real user searches are unable to succeed, we also want the health check to not be able to succeed. If we had separate pools, we could have a situation where the health check was succeeding and searches were failing. So we'd have a false positive. Or we could have situations where the health check was failing, but real searches were successful. So we'd have a false negative there. Mystery number 4. Why did everything work fine for hours before exploding? To understand this, you have to know what our search index's daily cycle was like. At the start of the day, the search index would be a certain size. And as our aggregation systems continued to discover jobs through the course of the day, this index would grow and grow and grow as we discovered new jobs all over the web. And then, at the end of the day, we would run a compaction cycle where we discarded all of the jobs that were no longer relevant and we pruned it down to only the active jobs. The payload size on the fateful day, specifically the list of job IDs, let's throw in a line for our 1 megabyte limit. It went like that. The number of jobs in the index grew steadily, and then at 11:32 p.m., a short time before I might have been saved, it broached that 1 megabyte limit, and everything went nuts. Lesson number 4, wait a few hours before declaring victory. This had been out for a few hours, said everything was good, went home, went to sleep. Oops. Then mystery number 5. Why did everything fail simultaneously? Anybody here from Denver? No? Denver mattresses went nuts yesterday. And then there's this dude in here who's trying to chase them down. I don't know what he's trying to accomplish, you know? So yeah, why did everything fail simultaneously? Not just for the Denver Mattress Company, but for me. If you look at what Indeed does from a high-level perspective, we crawl all of these job sites. We collect the job information from them and put them into a single database. From that database, we build an index of all the jobs that are active and we want to be searchable by job seekers. And then we take that index of jobs and we copy it out to all of the search services. So we build one index at one time and then roughly simultaneously propagate that to every single search service. That meant every single search service at roughly the same time got this index with just too many job IDs and started sending back those slightly too large payloads. So lesson number 5 is test your error conditions. I should have checked this 1 megabyte limit to see what happened, because a consequence of this that I didn't anticipate was it took everything down and it all happened simultaneously instead of being localized and recoverable. And then lesson number 6, deploy canaries for your major infrastructure changes. What we should have done was have a subset of servers using the new Boxcar protocol and a different subset using the old system. And we should have run that for days, possibly weeks. Because we didn't do that, that meant when Boxcar went down, Indeed went down completely, as opposed to just reduced capacity, which would have been the better way to go. If you want to go into a root cause analysis of this, well, actually there is no root cause, because all of these conditions had to occur simultaneously. We had to have that too low arbitrary 1 megabyte request size threshold. The health check had to request all jobs. We needed to have unbounded retries in the Boxcar client. And the index had to grow just a little bit too large. And then we had to have that closed connection on error behavior. And the list of job IDs had, repeating that. This is an old incident, but there are timeless lessons from here. One is measure actual values instead of inventing arbitrary thresholds. The mistake that I made was perhaps a mistake of poor experience, but there are a lot of people who don't necessarily have enough experience as well, and hopefully they can learn this with less difficulty than I did. Number 2, always limit how much data you request. Number 3, bound all loops. Number 4, wait more than a few hours before declaring victory. Number 5, test your error conditions. Not just does it do the right thing when everything's working, but does it fail in the way you expect it to fail? And then lastly, deploy canaries for major infrastructure changes. My mistakes can hopefully be your improvement. And then there's the final lesson, complex systems are complex, which Tristan and Alex will delve into more deeply. Thank you.